Welcome back! This is the third lecture of week 5 of Math 320. The topic of this lecture is the notions of lim sup and lim inf. Lim sup and lim inf are generalizations of the concepts of the supremum and the infimum to the context of sequences. If you don't remember very well the notions of supremum and infimum, this is a good time to go back and rewatch the lecture 1 and lecture 2 videos from week 3. The notion of supremum and infimum are defined for sets. They capture the ideas of the least upper bound and greatest lower bound respectively. The notions of lim sup and lim inf captures additionally the dynamic directionality of a sequence. They are in general quite different from the sup and inf of the set of values that is taken by the sequence. Try not to confuse the two notions. The material that will be covered in this lecture can be found on pages 60 to 62 of your textbook. I will mention this a bit later again, but we will do one thing slightly differently from the textbook. In your textbook, the author, Kenneth Ross, defined a notion for a sequence to converge to infinity, either positive infinity or negative infinity. For our course, we will not consider such notions. We will treat any unbounded sequence as divergent. A side effect is that we will not consider the lim sup and lim inf of unbounded sequences. If you're ready, let's get started. I will introduce the lim sup and lim inf in a manner slightly different from your textbook. The concept can be confusing the first time you see it in either presentation. I hope that by giving a different point of view in these lectures, you can contrast it against the discussion in the textbook and get a bit more out of the definitions than otherwise. As I said in the introduction to today's lectures, the concept of the lim sup and lim inf are extensions of the notions of sup and inf for sets to the context of sequences. A sup and inf are built from the concepts of upper and lower bounds, the sup being the least upper bound and so on. It is convenient to first describe how to extend the notion of upper bounds to sequences in a way that captures the dynamic motion of the sequence. To distinguish this notion from the normal upper and lower bounds, we will call them eventual upper and lower bounds. Let's give the definition. A number z is an eventual upper bound of a sequence if there exists some capital N such that for every index later than capital N, the term x sub n is no more than z. We can define eventual lower bound also just by switching the inequality sign. You see that the definition is almost the same as that of an upper bound, except that for an upper bound, the inequality xn is less than or equal to z must hold for all indices. But for an eventual upper bound, we only needed to hold for sufficiently large indices. The basic idea is that when thinking about convergence of sequences, we are only really care about tail events, meaning that we only care about what happens when the index goes toward infinity. So we can be perfectly happy with the sequence exceeding an eventual upper bound here and there, as long as eventually the sequence comes to rest below it. If you look at the definitions, quite clearly an upper bound, which requires the inequality to hold for all indices, must also be an eventual upper bound. We can just take capital N to be 1. The same hold for lower bounds. It turns out that if a sequence has an eventual upper bound, it must also have an upper bound. We can prove this theorem quite simply. If Z is an eventual upper bound for the sequence x sub n, then there is some index n such that all later terms of the sequence are no more than z. We can then let y be the maximum of all elements among x1 through x sub capital N. The maximum exists because this is a finite set. Now, if we take the larger of y and z, I claim that this number is an upper bound of the sequence. Given any term in the sequence, either its index is larger than capital N or less than or equal to capital N. If the index is larger, then by assumption, we know that the term is no more than z, and hence no more than the larger of z and y. If the index is less than or equal to capital N, then by our choice of y, it cannot be bigger than y, and the term is no more than the larger of y and z. An important caveat is seen in the proof. We have to take the larger of z and y. So it is quite possible that a given eventual upper bound is not an upper bound. The theorem only says that if the eventual upper bound is not itself an upper bound, we can find a larger number that is. Let's give an example working out the eventual upper and lower bounds for the sequence xn equals 1 over n. We start with the eventual lower bounds. First, we notice that every term of this sequence is positive. This means that every non-positive number, meaning negative or 0, is a lower bound, and hence, by what we discussed, is an eventual lower bound. I claim that no positive numbers can be an eventual lower bound. For given any positive z and index capital N, we can find using the Archimedean property a natural number small m such that 1 over m is less than z. By making m even larger, we can ensure it is larger than capital N as well. So we have proven that the negation of the definition of z being an eventual lower bound is true, and hence z is not an eventual lower bound. You may wish to rewind the video a bit or pause and open up the lecture slides in another tab to see that the condition we just mentioned is indeed the negation of the definition of z being an eventual lower bound. As a reminder, you can find the link to the lecture slides website on D2L. So this shows that the set of all eventual lower bounds of this sequence is precisely all the non-positive numbers. Next, we move on to eventual upper bounds. I first claim that none of the non-positive numbers can be an eventual upper bound. This is because every term of our sequence is positive, and so if z is a non-positive number, z cannot be greater than or equal to any term of the sequence, never mind eventually. On the other hand, if z is a positive number, then by the Archimedean property, there exists some capital N such that 1 over n is less than z. And since the sequence is decreasing, we conclude that z is greater than any later term in the sequence. And this shows that z satisfies the condition of being an eventual upper bound. To summarize, the set of all eventual upper bounds of the sequence is precisely all the positive numbers. Before going forward, here is a somewhat obvious statement. This property turns out to be quite useful. It says that given any sequence, any of its eventual upper bounds must be larger than or equal to any of its eventual lower bounds. To save some time, I include the short proof of this on this week's exercise sheet and will not discuss it in the video. Armed with the notion of eventual upper and lower bounds, we can define lim sup and lim inf. The definition. Given a bounded sequence x sub n, we will set lim sup of xn to be the infimum of the set of all eventual upper bounds of x sub n, and we will set lim inf of xn to be the supremum of the set of all eventual lower bounds of x sub n. Notice that the inf and sup used in the definitions are justified. If xn is a bounded sequence, then since any upper bound is an eventual upper bound, the set of all eventual upper bounds is not empty. Similarly, the set of all eventual lower bounds is not empty. By the useful property from the previous slide, any eventual lower bound is a lower bound for the set of all eventual upper bounds, and vice versa. So the set of all eventual upper bounds is a non-empty set and is bounded below, and so by the greatest lower bound property, its infimum exists. Similarly, the set of all eventual lower bound is a non-empty set that is bounded above, and so by the least upper bound property, its supremum exists. To get a sense what this looks like, let's return to the example x sub n equals 1 over n. The sequence is bounded. As we computed a few slides back, the set of its eventual upper bounds is exactly all the positive numbers. The set of its eventual lower bounds is exactly all the non-positive numbers. So the lim sup of xn being the infimum of all eventual upper bounds is the infimum of all the positive numbers, which is 0. The lim inf of xn, being the supremum of all eventual lower bounds, is the supremum of all non-positive numbers, which is also 0. As we will see later, in general, the lim sup and lim inf of a bounded sequence need not agree. That they are the same for this example is a happy accident. Here is a very important conceptual caveat. When we talk about the supremum of a set, we found that the set of all upper bounds of a given set, when non-empty, must have a minimum. We then set the minimum value to be the supremum of a set. We see that this is not the case for lim sup. We cannot define the lim sup as the minimum value of a set of all eventual upper bounds. We have seen in the example on the previous slide that a set of all eventual upper bounds may not have a minimum. For the sequence 1 over n, the set of all eventual upper bounds is the set of all positive numbers. This set has an infimum 0, but it does not have a minimum. So while conceptually the lim sup and the sup are very similar, there is one crucial difference when you are applying the concepts in proofs. That is, the supremum is always an upper bound of the set. The lim sup need not be an eventual upper bound of the sequence. The infimum is always a lower bound of the set. The lim inf need not be an eventual lower bound of the sequence. These are conceptual complications introduced by the fact that the sequences are dynamic. We will return to this and other subtleties of the lim sup and lim inf later in this course. Before moving on to some examples, let's introduce a very intuitive and useful property of lim sup and lim inf. Proposition: if a sequence is bounded, then its lim sup is at least as large as its lim inf. The proof follows quickly by putting together some facts we already know. For convenience, we will use U to denote the set of all eventual upper bounds of our sequence, and L for the set of all eventual lower bounds. From what we talked about a few slides back, which is now on the usable statement sheet as proposition 42, every element U is greater than or equal to every element of L. From this, we can conclude that inf U is greater than or equal to sup L. This was discussed as a property of the supremum and infimum in week 3, and we recorded it as proposition 26. Since these quantities are by definition the lim sup and lim inf of x sub n respectively, we have proven the proposition. Let's finish this lecture by showing a couple examples. First, we have xn equaling sine of m pi over 3. If we write out the first few terms, we find it to equal root 3 over 2, root 3 over 2, 0, minus root 3 over 2, minus root 3 over 2, 0, and the pattern repeats itself, with two terms of root 3 over 2 followed by a 0, and two more terms of minus root 3 over 2 followed by another 0. The set of all eventual upper bounds is the set of all numbers from root 3 over 2 and above. This happened to be also the set of all upper bounds of this sequence. There can be no other eventual upper bounds because the sequence keeps returning to root 3 over 2, and hence, if z is any smaller number, and capital N any index, you can always find a later term that comes back to root 3 over 2, which is bigger than z. Similarly, the set of all eventual lower bounds is the set of all numbers from minus root 3 over 2 and below, which also happen to be the set of all lower bounds of this sequence. Remember that the set of eventual upper bounds and eventual lower bounds may contain more elements than the set of upper bounds and the set of lower bounds. In this case, it turns out they don't. From this, we see that the lim sup of the sequence is root 3 over 2, and the lim inf of the sequence is minus root 3 over 2. And here we see an example of a bounded sequence for which the lim sup and lim inf are not equal. Next, we look at xn being minus 1 to the nth power plus 1 over n. This sequence is bounded. Since 1 over n is positive, and minus 1 to the nth power is at least minus 1, we see that minus 1 is a lower bound of the sequence. Since 1 over n is no more than 1 and minus 1 to the nth power is also no more than 1, we see that 2 is an upper bound. The set of eventual lower bounds for the sequence is every number less than or equal to minus 1. I leave this for you to verify as an exercise. You should try to follow the argument given earlier for the sequence 1 over n. The set of eventual upper bounds for the sequence is every number strictly greater than plus 1. I summarize the proof here. First, we show that if z is less than or equal to plus 1, then z cannot be an eventual upper bound. This is because at every even n, x sub n is equal to 1 plus 1 over n and strictly bigger than 1. So given any capital N, we can find the later index, say twice capital N, which is even and for which x sub twice capital N is strictly larger than z, disproving z from being an eventual upper bound. Next, we show that if z is more than plus 1, then z is an eventual upper bound. This is because z minus 1 is positive, and so by the Archimedean property, there is some capital N such that 1 over capital N is less than z minus 1. Rearranging the inequalities, we see that z is larger than 1 plus 1 over n for any later index n. And 1 plus 1 over n is larger than x sub n, since minus 1 to the nth power is never more than 1, and so z is an eventual upper bound. From these computations, we see that the lim sup of x sub n is plus 1, and the lim inf of x sub n is minus 1. Okay, that's it for this lecture. See you next time.